Hello everyone, thank you for being here. I want to thank Professor Florentino for having organized this course. Also I want to thank the CMAF, FCT and the University of Lisbon for giving me this opportunity. In this course I will give you a very crash introduction to the theory of Gromov-Witten invariants. In the first lecture, we will cover the main definition. And in the second lecture, we will see a more specific example, which is the case of genus 0. So we will talk about boundary divisor and so on. Since the aim of the course is to introduce just very basic ideas, so again, boundary divisor, potential, and so on. We will focus only in the best scenario case, so with the hypothesis of genus 0 and the target being an homogeneous variety, or more generally, a convex variety. In the third and fourth lecture, we will focus on the quantum cohomology ring, and we will see some application. Enumerative application. So let's start. I want to recall that all varieties are over C. Let's start with the definition of convex variety. So let X be a smooth projective variety. We say that X is convex if for every morphism mu from P1 to X, we have that the H1 of P1 mu upper star of the tangent bundle of X is 0. A lot of varieties are convex. So let's see some example. The quotient X over G sub P, where G is a complex Lie group and P is a parabolic subgroup. This is always a rational homogeneous variety and a projective variety. So space of this type are convex. This includes projective space, Grassmannian, flux variety, and so on. A remark, all varieties of this type, G sub P, are rationally connected. So they have a lot of rational curves, which is what we are interested in. What does it mean that it's rationally connected? That for every P and Q in X, there exists a rational curve through P and Q. So every G sub P is rationally connected. Every G sub P is also convex. It's natural to ask is if the converse is true. So, question. X convex and rationally connected imply, this is the question, if X is an homogeneous variety, G sub P, where there is a result of Panderi-Pande that said that this is yes, the answer is yes, if X is a complete intersection in the projective space. Let's try to move on since we are already late. Okay. Just to recall you that if C is a smooth projective curve of genus G, is zero if and if the automorphism of C is three-dimensional, particularly PGL 2+1. Basically because C is P1 in this case. Then when we have G equal to 1, the automorphism of C is one-dimensional. And when G is of genus at least 2, then the automorphism of C is finite. And moreover, let's recall that when we have a map from C to some variety X, then we have an induced map in singular homology. X, Z. In particular, when X is the projective space, the singular homology is Z, and the image of the fundamental class of C is the degree of the image of the map mu. So in this case, mu lower star of C is the degree of the image of C, of the image of mu. Okay. So just to recall that. Is still readable to? So I leave this blank.
Yes.
If there is any questions, please ask me. I know I will repeat myself. Today will be mainly definition. We will see a very few examples. But I promise it will be more interesting since. Okay.
So one question. So the theorem of Panderi-Pande. So if X is a complete intersection, it has to be one of those two.
If in addition is a complete intersection, this is convex, rationally connected, and complete intersection. Then
it has to be
is a homogeneous variety. If G is X is in addition. in addition to this and this. Just completing the section on homogeneous varieties. Okay. Definition. Endpoint. Use G. Quest state. Earth. Yeah. Is a projective connected is C of G and this singular okay. An endpoint genus G quasi-stable curve is this object where C is a projective connected reduced towards nodal curve and of arithmetic genus G. We allow nodes, and P1, Pn are n distinct non-singular point of C. This, in some sense, is the main object for us. I mean, the objects that are parameterized by n bar are this this tuple of objects, a curve plus n point of the curve. Okay. Okay, this is a single object, but we know that we may consider a single object, but in families. So let's see what is a family. The definition: let S be an algebraic scheme. A family of this one. Don't let me to rewrite. Of this one, of any continuous G quasi-stable curves over S. I mean, it's a family of that object over S is flat, is a flat projective map with n section P1, Pn such that each point S, meaning closest point, so S is back of C, fiber and each fiber over a closed point, CS P1 of S, Pn of S, is a n-pointed genus G quasi-stable curve. Okay. Here we defined a single object, and here we are defining a family of this object. So we have S, and over each closed point of S, which call small s, here we have this C, MAT-PUR C, and the fiber is a curve C with that properties, and in addition we have n section of this map P. So we have P1, P2, and so on, such that the image of small s are n smooth point of C. So here these are point of C. Here we have section that at each closed point give us the non-singular point of the curve. So this is a family. Okay. Okay, now we have two more definitions. Okay, I leave this down. Okay, basically, I mean, it's less boring if I justify the definition. This is a definition of curve with points, and now we have to give the definition of stable maps, which is basically the same of this, plus here we are going to add mu, where mu is a map from C to our best points, to our space of where we need to study the stable maps. So definition. So we see the definition of stable curve, the definition of family of stable curves. Now we are going to see the definition of stable maps, of stable map, and the family of stable map. Okay. Let X be again an algebraic scheme. This will be again the scheme, the variety where we study the maps, the rational curves. And for the moment, we don't suppose it's convex, but later we will. Okay. A family let's give directly the definition of family. So, a family of maps, stable maps, over S from n pointers genus G whose X consists of the following, of the data. Of the data E plus PI and mu where a family of n pointers genus G, quest table, groups, and section. Okay. We still use quasi stable because later on we will give the definition of stable, which enter more in how this mu behave. Yes. So basically is this definition plus amorphism mu from C to X. And the definition is quite logical. It's a family, as like before, and amorphism. Simply amorphism. Okay. Here I have to give the definition of isomorphic families, which basically isomorphic families means another family over the same base with an automorphism that makes these maps commutes. I mean, are quite common, this type of definition in algebraic geometry. Okay, let's give the definition. Okay. There are questions from Zoom? No.
But I have another question, actually, but from the definition of complexity. Why do you write in terms of H1 when it's over P1? You could write it just in terms of degree, no? The degree of the pullback map, the pullback line bundle is positive, right? That's what. No?
It's not the line bundle. I mean,
Every map.
Every map, yes, but not select bundle, it's the tangent space.
it's a machine, it's the back, and it's bundle, guys.
Yes. But that's the same thing, the same degree.
Okay, what I think what you mean is that these splits, no?
Yeah.
And each one of these is positive.
Yeah.
Yeah, but it's equivalent, but I have to say that this splits is
Okay.
the same of these.
Okay. Good.
Okay.
Thanks.
Okay, I will try to be fast here. Two families of maps over S. Okay, let's keep on S. U. Okay, the other one is the same, just up here, here. Okay, so we have two families. The first one and the second one, which where we keep this equal, S and X, are isomorphic. If there exists a scheme isomorphic, so no fish tau from C to C prime such that E it's an isomorphism between the base C and C prime, making everything commutative. This is an isomorphism. Simple, I don't know if it's called definition of remark. Any point genus G versus stable curve C E1 EN mu is a family over spec. So this is basically the definition of a single quasi-stable maps. It is this one when this S is just a point. So when this MAT-PUR C is actually a curve. Okay. Oh, now we are closer to the actual definition of moduli stable maps, because now we define what is a stable family of maps. So all of these one are quasi-stable. To define what is stable, we have to look into these maps map mu. So definition. The map C E1 EN mu from C to X is stable if for every component E of C mapped to a point. So for each component that is contracted, if E is a P1, E contains at least 3 points among marks and nodal points of C. 2, if E has arithmetic genus 1, it contains at least 1 point among don't me let to rewrite the same thing among the marks and market point. This is we repeat here. So maybe it's better to give geometric example of what this definition means. So imagine we have a map C. C can be P1. P1 topologically if S2. This is diffeomorphic to S2. C can be this one of mean of genus 1. Can be of genus greater than 1. For example, can be nodal. So, for example, can be this, which topologically is this one. I mean, it's this when we contract a circle. Can be the gluing of this one. Can be this, for example. So, two components glue at a point where this is of genus 1 and this is of genus 0. For example, these are all examples of C. Then we can have market point, for example, this. I will use another color for market point. This cannot be a market point because it's a singular point. So this cannot be. Okay, so imagine we have mapped from each one of these objects to, let's say, to P2, for example. Okay, if this is not contracted, then everything is okay. It's not only quasi-stable, it's stable. If it's not contracted, okay. And this is valid for any genus. The problem is when we have contracted components, in order to be stable, and not just quasi-stable, we have to see how the contracted component behaves inside C. Okay, so for example, we may have a map from this object when this part is contracted and this not. So we have this component that is mapped to a line, and this is contracted to a point. This is stable because the contracted part has genus 1, but have two points among marks, which are because it's a map, a market point, and it has a singular point, so has two. For example, if I have this one and this is contracted, and I have 0 market point, this is not stable because I have 0 point among marks and market point. In order to have this stable, I need at least 1 market point. Now this is stable. And if I have this one, this is P1, no? And this is an elliptic curve. So, if this is contracted, this is not stable. In order to be stable, I have to add at least 3 market point. But why? What is the reason of this? The reason is that I want my quasi-stable map to have a finite number of automorphisms. Now, this has three-dimensional automorphism group, PGL. So, an automorphism, by the definition, is a map from P1 to itself that preserves the market point. So, since this is three-dimensional, you have to impose three conditions in order that this three-dimensional variety shrink to a finite, something that is finite. This, without the market point, has one-dimensional family of automorphisms, and with a market point, the automorphism that preserve the market point are a finite number. So again, I have a finite number. This, even without a market point, has always a finite number of automorphisms. So I don't need to add the market point. I can, because the identity is always it's always the automorphism group of a market stable map, quasi-stable map, is always well defined. So I can add as many points I want, but in order to the automorphism group to be finite, 0 is enough. So this is the reason of this definition. So these are just the conditions we need to have a finite number of automorphism group of the of our quasi-stable maps. Okay. There are no other questions? We are quite late. Can I go through? Okay. As you imagine, definition. Not that here, this is not.
It's fine for the pictures.
Okay.
Please don't write letters.
Okay.
Yeah.
Here, we are not considering curves inside the X. We are considering maps with target X. This is a very important remark, but we will explain more this later. Okay. Okay. Definition. Let it be an algebraic scheme again, and beta a cohomological class, yeah, homological class of a curve, but any class. We define the contravariant functor. This character is calligraphic, which cannot be confused with the Roman one. So these are two different objects, and I use the calligraphic one to functor and the normal one to schemes. Okay. It's beta. From the category of schemes over C, the category of sets. And it's the functor parameterizing stable maps. Stable maps to X. So from S to. Okay. C, B, S, B1, N, U. Okay, these stable families over S with fixed okay, this N it's here. So the N here is the number of sections, and the G here is the genus of genus G. So, and beta here is such that mu lower star of C of each fiber is equal to beta. Okay? So we have half hour more, no? It's
Maybe 20 minutes, is that fine? No, sorry. Half hour plus 10, 15 minutes.
yeah. Okay.
Because we started like 10, 15 minutes.
Yes.
Later.
Theory. So we define this function. This function is representable by a course moduli space. Instead of give the definition of functor representable from a course moduli space, I just give directly the theorem that says that. Okay, let X, an algebraic scheme, be projective. And MGN X beta is representable by a projective scheme which use the same M but with a different character, GN. Maybe better to use bar. Bar. Because without bar we mean another things that we will define later. MGN, X beta, and a functor mu MGN X beta. This is the functor to form in the category of schemes MGN X beta, such that one. Okay, this is the first property what in some sense justify everything. Mu of spec C, so from MGN X beta computed in spec C. So what is this object? Just this one. So we define this functor. We are computing this functor at spec C. Here, spec C. So what does it mean? That this is a modulo isomorphic. That this is the whole set of stable maths, because are the stable maths are not over S but over spec C. So the stable maths, not stable family. So all the set of stable maths is a bijection. Bijection of sets. So, first property of the definition of a representable functor. The functor is representable if there exists a projective scheme such that the closest point of the projective scheme are in bijection with all the set of stable maps. So we have a scheme that parameterizes all stable maps, not in families, unfortunately, but at least that are family over spec C. Okay, this is just a compatibility condition. If zeta, in some sense, this is because of unicity. If zeta is a scheme and C is a natural transformation of functors, then there exists a unique of schemes gamma from MGN x beta to zeta such that I will continue here, such that C equal to gamma tilde composite P, where gamma tilde is the natural transformation between these functors. So this second property means that if I have another, let's say another scheme that parameterizes that object, then there is a map from M bar to zeta. Okay. Questions? This is the definition of representable functor by a coarse moduli space. That's a standard definition. But instead of give the definition, it gives directly the problem, the theorem. Okay. This is quite technical, very theoretical, and we will not use it so much. But it's very, let's say, it allows us to give immediately some properties. So, corollary. The corollary of this big theorem, which is quite difficult to prove. Corollary. There are natural morphisms AV, the evaluation maps so n is the number of sections I fixed. Yeah. Okay, maybe it's better if I give not only the map, but easy description of what this map does. So, I have a functor with a coarse moduli space that parameterizes object of this type. A course C, a map from C to X, which is stable. So we have the domain of mu, which is C, with a bound with n marks. And eventually have the image of mu. So this object, where mu of C is beta. So this basically means that the image of mu is of fixed degree. Okay, what is this AV? It simply maps this object. Okay, let's give a number to each market point. 5. AV, let's say 2, for example, of this stuff. So here I have the second market point, which have an image in X under mu. So by the Functorial property of M bar, I can construct a map of this type, which simply take the second mark, the first mark, it depends on I, and map to a point of X. Okay. So I have a second map, which is the forgetful map. I have here n plus 1 maps. Here I have just n maps. C, P1, Pn. So I forgot the n plus 1 map and leave everything equal. So what does this do? It's simply. So I have this map, and what it does is take this and define a new map where I have the same C, but forgetting one of the marks, in this case the last one, but so I have just 4. And leaves the rest equal. Note that in general, C could need to change. In the sense that, for example, if I have let's suppose that this is C. And mu contract this map. So this is contracted. And I have just an image of this component. This is not contracted. So what happens is if I forgot this mark, that I have this sorry. So I repeat. I have a component that is not contracted and I don't care. And I have another component of genus 0 with 2 market points. But this is connected to C with a singular nodal point. So I have 3 components. So if this is contracted as is this, there is no problem because it's stable. Okay, so I have the image here of the not contracted part. What happens if I forgot one of the mark? That this component now has just 2 points among the mark and singular point. So if this is contracted, this is not stable. So what happens in this case is just that this is let's say excluded from the domain, and the market points stay only in the part that is stable. So what happens is that if I forgot one of the market point, this is not stable anymore. So it must be contracted. So this C can be changed. 3. New. This is not new. This is new. It's the other one. Maybe I can change the notation. Let's use that for now. MTN x theta to MGN. This is the moduli space of stable curve. This is quite no object, you know. Let's say, forget mu. So since C, P1, Pn, mu, to C, P1, Pn. So, forgot this part of the story. I remember just that. Clearly, this is defined only when this space is defined, which is when 2g minus 2 plus n is greater than 0. In this case, we have this map. Okay. Proof. Use part 2 of the theorem. And this corollary is immediate with part 2 of the theorem. So I leave for you. Okay. In the last 10 minutes, I will give you a more geometric example in order to this stuff to be clear. And moreover, it justifies why we will only deal with this space when G is 0 and X is the projective space.
So one question, I guess this is well known, but this moduli space you mentioned is a coarse moduli space. Are there any cases where this is a fine moduli space? Yes. This universal bundle.
Yes.
Something. So.
I mean, no. For example, when in the case of Grassmannian, when beta is line. Okay, we will see this later, but the answer is yes. This one could be fine moduli space, but in general, it's coarse. Okay, remark. M, G, and X beta can be still be for G greater to 0. So we will see a specific example. The example is this one. M, okay, genus 1, 0 market point to P2 of degree 3. So this 3 is here, this 3 is 3 times a line. So this means MAT from a course of genus 1 such that the image is a cubic. Okay? Okay. There is something I didn't define yet. Okay. Okay, it doesn't matter. Okay, this has 2 components. So this is a coarse moduli space. So it's a projective scheme. And this has 2 components. of dimension 9. Okay, let's see who these components are. Okay, this is the subset parameterizing curves with irreducible domain. Okay, so this parameterizing maps -1, degree 3, degree of the map mu, where the image is a cubic. Okay, the space of cubics in P2 is 9-dimensional. So, how many maps do I have? Take a cubic in P2, and I have a 9-dimensional variety where I can choose. A cubic in P2 is a curve for genus 1, so I can imagine an isomorphism from this to a curve of genus 1. And if I have another curve with the same image, so this is mapped to a point here, and this is mapped to a point here, it's very easy to see that there exists an isomorphism from this domain to this domain, making this diagram commutative. This implies that for each curve, for each smooth cubic in P2, I have a map. So since this is 9-dimensional, this is also 9-dimensional. Okay? Okay, so the space of smooth cubics in P2, cubics, is 9-dimensional, so basically each map is identified with its image. For each curve, here I can imagine a map with that image, and for each map here, I can consider its image, and this is one-to-one correspondence. But I have other way to construct stable maps. Consider this space. So I have the same space with the one market point and degree 0. So it's contracted. Okay, let's just finish, and I have explained later what I'm doing. So consider this Cartesian square. P2. Okay. So take this space, that is the space of maps with genus 0, and one market point, mapped to P2 with degree 3. So, since the image of a rational map in P2, if has degree 3, it must be singular. So this is the image. Cannot be smooth because a cubic in P2 is of genus 1. But I have genus 0 here. So the image cannot be of genus 1, so it might be of genus 0. So this is the image. And here I consider the maps from genus 1, one market point, and of degree 0, so contrasted. Not that this is perfectly fine, because this is stable, because it's genus 1 with one market point. I consider the evaluation map here. I consider the Cartesian square, and I get this space. What's this space? This space is just the space gluing this one. So I glue them at the market point. So this is the same. This is contracted, and I glue them on the market point, then construct this space. What's the dimension of this space? It's so dimension of this one. Okay. The dimension of this P2, 3 plus dimension of this 1, 1, P2, 0 minus the dimension of this one. Okay, what's the dimension of this one? Okay, how many singular cubics do you have in P2? 8. Because it's just this space with the condition to be singular, which is one condition. So if this is 9-dimensional, this is 8-dimensional. But I have a market point here, so the dimension is one more because I have a market point. So this is 8, 1 plus 1. So what does it mean? I have a 8-dimensional space. I consider for each curve a P1 mapping to that curve, but I have also a market point, and whenever I choose a market point, I increase the dimension of 1. So this market point gives me one more the dimension which I expect. So this is the dimension of this is 8 plus 1. Image plus the choice of the market point. This is basically the choice of the image. So this is 2-dimensional. Minus P2, which is 2-dimensional. 9. So this is also the same dimension. Basically, here it's the choice of the image plus the choice of where I put this singular point here. And so these two spaces are of the same dimension. So I have two components of the same dimension. We will see that when we choose G equal to 0 and X convex, this doesn't happen. The Moduli space is well behaved, irreducible, not too much singular of the expected dimension. just expected dimension of n bar g n is beta, which it's just expected. That is what will be if everything works, but it's not always that. Is minus kx times beta. This is the canonical divisor of x intersected with beta plus dimension of x minus 3 times 1 minus g plus n. So when g is 0 and x is convex, the space is of the expected dimension. In general, it's not. We may see a component of it's not purely dimensional. It's not irreducible. It's not reduced. And in this case, this number is 9. But in general, it can be the same. So I think I can stop here. Next time, we will focus only on the case of genus 0. And we will see more examples of this. Okay? There are no more questions?
Okay. Thanks. Questions? Also questions from the viewers that are by streaming.
Are there any?
No.
Okay.
Not for now. Let's see.
Okay.
So questions.
So you said there about the genus 1. It's like every cubic in P2 genus 1.
Smooth one, yes. Every cubic in P2.
Can you remind me how you compute the genus? Like the dimension of the base is 9.
Genus is 1 over 2, d minus 1, d minus 2, when d is the degree of the curve. And in general, you have to consider the singular and the nodal and the other one is cuspidal component. Plus cuspidal, minus cuspidal. So when it's smooth, you don't have this, and this is the genus form. So for line conics is the genus 0, and for cubic it's 1.
It's called degree genus formula.
Yes.
It only works for, if I'm not mistaken, it only works for curves in P2.
Yes.
Smooth curves.
Okay, so higher base also.
And you need to subtract some numbers when you have it. It comes from this Giosuè theorem.
Yeah, maybe also from Riemann-Roch, I think.
So if degree is 3, you get
1, yes. Okay, so if there are no more questions, thank you.